is. So Einstein said that means there's no such thing as absolute space, which kind of follows if you think about it. But that's it's a cool but difficult thought process.
Right. I mean, that's essentially what's happening when you're on a plane. I mean, if you're throwing a ball up in the air and catching it on the plane, it's happening at a much smaller scale, right?
Yeah. I mean, you're flying at whatever, 600 miles an hour relative to the ground.
But it doesn't seem like it when you're sitting there.
Yeah, and Einstein elevated that to a principle and said, if you're moving at if you're not accelerating, you're just moving at a constant speed in a plane, or now. I mean, that's essentially what we're doing now. We're moving around the sun at effectively constant speed. Then you can't tell. So there's no experiment you can do. We could look at the decay of a radioactive nucleus or some electricity and magnetism or bounce a ball, have a pendulum, whatever it is. And there's no experiment you can do to tell you whether you're moving or not. Therefore, that concept has no meaning because you can't measure it. And that's led Einstein to relativity.
Wow.
So that's the basis of general relativity, which is our best theory of the universe.
Now, why is it that we think that the known universe is larger than we can observe?
Well, one point is that it's expanding, and we always see the same radiation out there, so the glow of the Big Bang. But there are some deeper reasons. The one from the theory of inflation, the best way to explain the universe, the properties that we see, is that it's very much bigger than the piece we can see. So, for example, we measure space to be what's called flat. I don't even have to say what's called flat. It is flat. So if you imagine slices of space, let's imagine slices of them at different times. So you just slice the universe and say, there's a big sheet. It's like this table.
Okay, like a table.
There's a sheet of space, and there's another sheet, and another sheet. And it can have a geometry, right? It can be flat like a tabletop, or it could be curved like a sphere, or it could be curved in the opposite direction, sort of like a saddle or a bowl. And we can measure that. And when we measure it, we see it's absolutely flat. And that's a very unusual thing for it to be like. It requires, because what Einstein's theory says is that the shape of space, that the curvature of space is determined by the stuff that's in it. That's basically Einstein's theory of general relativity. Put stuff in space and it curves it and bends it and warps it and stretches it and so on. And what we find is that there's precisely the right amount of stuff in the universe to have a completely flat universe. And the explanation, the most favoured explanation for that, is the universe is way bigger than the piece we can see. And so it's like looking at a piece of the Earth. If you look at a little 1 mile square of the Earth, right, then it's flat, right? You have to look at big distances, kind of order the radius of the Earth, or not, bigger than 1 kilometre anyway, or 1 mile, to see that actually you're on a curved surface. And that's one of the ideas about the universe and why it appears to be the way that it is, because it's way, way bigger. So we're just looking at a little piece, and that's why it looks flat. And that's one of the ideas.
Now, when you say flat, like that, my brain doesn't understand this. Because from our perspective, when you look up at the Milky Way, you see all these stars all over the place. So if you're saying flat, like how much height and what are you saying in terms of like the way to measure it?
The best way to think about it is not to think of 3 dimensions of space, because then we can't picture it.
Okay.
But you can think of 2, like this tabletop, and that's all right. We just forget the other one for now. And so you know what flat is on this table. I mean, you could define it. So you could say, for example, that if I draw a triangle on the top of the table, then all the angles add up to 180 degrees. So that actually defines flat. If you did that on the surface of the Earth with a big triangle, then the angles wouldn't add up to 180 degrees. Or you could draw a circle and say, what's pi? So pi is the ratio of the circumference of a circle to its diameter. That's only true on a flat surface. It's different if the surface is curved. So you can define flatness.
So when you're saying flatness, what is the height and what is the width? Like if you're talking about it as if it's a table, there must be some sort of there's a dimension to it, correct?
Oh yeah, there's a third dimension of space,
right.
But the same applies. It's just a generalization of geometry. Then, so you can the point is we can picture it in 2 dimensions, but you can draw. You can quite literally, you could imagine sending light beams out, and we do this measurement actually. We can look at the most distant light we can see